So our next speaker is Verilog from Texas A&M University, where he's a PhD student. His research focuses on developing more efficient and automated hardware fuzzers to detect vulnerabilities in processors and SoCs. He has won Quality Graduate Student Award at TAMU in 2023 and several other student grants. And the title of his talk is Hardware Fuzzing to Secure Modern Hardware. Okay,
Thank you.
Thanks for him.
Okay, so hello everyone. Thank you for being here for my talk. So as you said, we'll be discussing today about hardware fuzzing. Now, I was talking with multiple attendees here today since morning, and I was telling them, okay, I do research on hardware fuzzing, and a lot of attendees did not really know what fuzzing was. So I think this is a good opportunity for me to explain about this research. So essentially, fuzzing is a new type of hardware verification technique. And what we are aiming for is we want to make verification faster, we want to make verification efficient and automated. And I will discuss how we do that in the subsequent slides. Okay. Okay, so very briefly, my talk will be in three parts. First, I will just talk about briefly what is security vulnerabilities, and then I'm going to introduce what exactly this hardware fuzzing is and why it works. And then I will also discuss about some of the, so along with part two, I will also basically use the hardware fuzzer that we developed to explain that. And in part three, I will be discussing briefly about some of the new hardware fuzzing techniques we developed as extensions to the base one. And essentially, my goal is to show the promise of this fuzzing techniques and the kind of advantages they have and when we are verifying hardware designs. Okay, so let's start with part one. I think this slide is pretty much familiar with everyone. We have hardware designs, lots and lots of hardware designs, but then there's also so many hardware vulnerabilities that are being detected every day, every year, even in processors from ARM, processor and Intel, we see new vulnerabilities popping up. And no one likes these vulnerabilities. Like companies don't want the vulnerabilities. It's going to damage their reputation. Users don't want vulnerabilities because they want to secure their data. And what makes things worse is that vulnerabilities in hardware are harder to fix. Like you can't really patch them. Even if you patch them, you're going to have to compromise on some type of performance because most probably you'll be turning off the feature. So the main research goal for us was how do we make sure that we detect as many vulnerabilities as possible at the pre-silicon stage? Now, when we started research on this line 5 to 6 years ago, one of the major challenges that we faced was that there was a lack of awareness as to how hardware vulnerabilities look like. And also, even if we somehow develop a tool, like how do I verify it? How do I make sure that this tool is able to actually find vulnerabilities? So for that, what we did was we started this Hack the Silicon competition series. It's basically capture the flag competitions. These type of competitions are popular in software, but you don't really have a lot of hacking competitions for hardware. So we wanted to start that. And we organize these competitions in popular conferences like DAC, EOSNIX, and Chess. And the goal here is want to promote hardware security verification. We collaborate with partners like Intel, and essentially we ask them, hey, what type of vulnerabilities do you see in your Intel designs? And we try to replicate them in open source risk-free SoCs, obviously because we won't get access to commercial designs. And then we design a buggy SoC, we give it to the participants, and we let them find the bugs. So that is the competition. They'll bring back the bugs to us, we'll evaluate them and declare who the winner is. Now, we have been doing this competitions for multiple years. It's one of the biggest hardware security competitions in the world. Um, we inserted lots and lots of vulnerabilities. Now, this not only helped a lot of researchers understand what vulnerabilities are, but it also gave them essentially a platform to evaluate how good their techniques are. And we open source the buggy designs with these vulnerabilities, like they'll be there on our website. And in fact, the MITRE CWE, or the MITRE organization that maintains the CWE database, they actually used a lot of the vulnerabilities that we inserted in the competitions as examples in their website. So if you go and look at hardware CWEs, when they list the actual hardware design example, like a lot of them will be from what we inserted in the competition. And we are very happy that researchers are able to use those examples to develop the tools. Okay, so that finishes the first part. Now I'll get into hardware fuzzing. Now, so how do we transition from here to hardware fuzzing, right? So while we are organizing the competitions, one thing we also noticed is every time we give a design to the participants, the first thing they do is manually inspect the design. Like, let me look through the Verilog code and see if I can find bugs. But this is not really the case when you look at, let's say, a software hackathon competition. They're going to start using tools to find, like, make sure that, oh, let me see if the program crashes or something like that. And they could do that, and we are not able to, is mainly because how fast and how automated some of the software tools are. And one of the popular ones is fuzzing. Like, you go to any software hacking competition, the one thing that everyone tries is fuzzing. So it's basically a verification technique. It generates inputs, tests it on the software, and sees if the software crashes or fails or throws some type of errors. And this is very popular in software security. It's been very successful for multiple decades. There's lots and lots of research papers on that. And our goal was, okay, if it is that successful in software, will it also work on hardware? So, and basically the idea here is that you have random testing, which is something very fast and automated, but it won't give you like the full coverage. You have formal tools in hardware. They are very good at like verifying specific regions in hardware, but if you want to use it for all the coverage points, it just takes forever. So fuzzing is basically wants to be as fast and automated as random testing, but also have as much coverage as we get with formal tools, like the precise coverage that we have. And the idea for doing that is through the fuzzing, which the software domain has adopted. So at the heart of fuzzing techniques, we have something called coverage metrics. So basically, before I introduce fuzzing, I just want to give a brief overview on this. So if you take any type of hardware design, it will have different types of components. But what you'll see is they consist of flip-flops, they consist of combinational logic, and they consist of sequential logic, like again, registers. And then there will be control logic that drives, let's say, for example, the select signal for the muxes, and there'll be pure combination logic. Now, if you want to understand what exactly is happening inside the hardware, you can classify all those different components into types, and then you have coverage metrics. And I'm pretty sure this is very familiar with everyone here because we are all from hardware verification background. You have the set of code coverage metrics. It's been there for a very long time. All the commercial EDA tools offer this. So oftentimes, the code coverage metrics is only used to say, okay, I tested my design for 1 day, 2 days, and I got 90% coverage. It means that maybe it's more or less ready to go to the next stages. Now, this same coverage metrics that is being used to just evaluate how good the design, how much verification we did on the design, what fuzzing does is, rather than just treating coverage as a final report, it uses it for generating the inputs. So this is all the components that the fuzzer has. Some of the things that we are familiar with, if let's say we consider random regressionist, you will have test cases that you generate randomly, you'll have a design and a test, you'll have some type of a reference model that you compare with to find bugs. So these are something that we already know from random regression. Now, what makes fuzzing special is these parts on the left. So fuzzer starts with randomly, again, it also randomly generates input. Like we assume that it knows the grammar, it knows the ISA, the instructions. The first input that it generates is random. But once it runs that input on the DOT, it immediately looks at the coverage. So it sees what activity is that input causing. And based on that, it creates a feedback data. It passes feedback to something called a mutation engine. Now, mutation engine is a block that takes the current input, it modifies it slightly. It's what is called mutating the input data, and then it generates the next set of inputs. So you don't keep on randomly generating inputs. You randomly generate one, and then if it's doing well, then you do mutate it, then you get the subsequent inputs. And if you encounter an input that is not really increasing coverage, so it's not really good input, so you throw it away. The feedback engine makes sure that it throws away or selects the inputs based on how the hardware is reacting to those inputs. So this is one part where it makes the fuzzer more automated and more efficient. Automated because we no longer have to write any inputs. The starting input, the subsequent inputs, the directed testing is all taken care of. And it's also efficient because even though it is generating the inputs automatically, they're more meaningful. And every input that it generates, it tries to cover new regions. So this is a very basic framework for hardware fuzzing. This was the first fuzzing framework that we developed. We published this in Usenix 2022 conference. And with this, we were able to show that yes, hardware fuzzing does work. Sorry, fuzzing does work on hardware, not only software. And we more or less were able to achieve our goals. We made it compatible. It works with like different types of RTL languages, different types of verification tools, including commercial tools. And we made it automated. Like we did not have to actually give it any input to try. And then it's very practical in the sense that now we give this tool to students at Texas A&M University as assignment in our hardware security class, and they have no issues running it and collecting coverage and things like that. And it was also efficient. We found a lot of new bugs. We tested it on popular risk-free designs, and it was able to find 11 bugs. We were able to file 5 CVEs for these vulnerabilities, and it had like 2x more faster in terms of coverage correction compared to random regression, the traditional technique. So this highlights basically the novelty of fuzzing, and it showed that yes, fuzzing has potential and it's worth exploring more into this topic. Now with that success, basically we used our first hardware fuzzer as a baseline, and then we went ahead and developed multiple extensions to fuzzing. So yes, it is good. Yes, it is automated and it works. But then if you look at the various components that it has, there is still a lot of scope for improvement. Like for example, I said there is something called mitigation engine. It modifies the inputs to generate the subsequent inputs. But it has a lot of choices as to how it can mitigate that input. And with our first version of the fuzzer, we used some static optimization decisions to tell, okay, this is how you mitigate the input. But then if you want to make it more efficient, you can use learning algorithms. Like for example, we use multi-amp bandit. Multi-amp bandit is it's basically a very well-known learning technique where if you have 10 choices, each of them have their own reward. You want to know which choice is the best, then you can use algorithms like that. And we were able to use it on the mitigation engine, and we created a new multi-amp bandit fuzzer. We have a hybrid fuzzer that we developed. I'm going to discuss about that in a second. And there was this particle swarm optimization that we used. Um, so multi-amp bandit, we used it for seed generator. So seeds are basically the inputs. And every time the fuzzer runs, it has a choice of inputs that it can pick from. That's what MAB fuzz does. And PSFuzz was actual one that decided which mitigation techniques to use. And we also did some more extensions where they focus on other types of vulnerabilities. So the base one was for functional vulnerabilities. We also had Whisper Fuzz and Specure. These are focusing on timing and speculative execution related vulnerabilities. So for that, we had to change the vulnerability detection a bit. Like you can't use golden difference model differential testing to find, for example, timing vulnerabilities. So the vulnerability detection mechanism was different for that, and that's why it's a different hardware fuzzer. So I obviously can't go over all of them. I'll just go over one of the hardware fuzzers that we developed after our first one. So this is HyperFuzz, and it's actually very interesting because one of the age-old questions is, I have techniques like fuzzer or random regression where you run simulations, increase coverage, and you have tools like, okay, I have formal tools, like for example, I have a Jasper Gold tool. Now I can use that, or I can use this, but which one do I use for how much time, and which one will give me better results? So you basically want to optimize things, right? So hybrid fuzzer, the HyperFuzz that we developed, basically we try to automate the entire process. It has the fuzzing component that does regression testing. It has the formal component where, okay, you have one particular region in the hardware, you want to formally prove it. So we added the glue logic in between because obviously for Synopsys VCS does not talk with, for example, Cadence Jasper Gold. So we added the glue logic in between. So we said we'll run the fuzzing and we will see what type of coverage points it is having difficulty to cover. And then basically we have a scheduler that determines when we should switch from fuzzing to formal. It selects the coverage points that are not yet covered, and it converts them into something called properties, like the assertions that formal tool is familiar with. We give it to the formal tool. If it's assertions, it knows what to do. It gives Boolean assignments like waveforms of input signals saying, oh, you need to use these inputs to cover that one point that you're missing. And then we have test case converter. We give it back to the fuzzer, and the fuzzer continues doing this. And then the scheduler makes sure to properly switch between the two techniques. So this was again more effective than just doing fuzzing. In fact, it was orders of magnitude better than simply doing fuzzing, and it was also able to detect new vulnerabilities. And we showed it on different types of code coverage metrics just to show that all the process that we do here is automated and it works for different types of code coverage metrics that are used in the industry. So again, I'm not obviously going to go into other hardware fuzzers that we have. So these are the different other hardware fuzzers that we developed. Each of them showed a lot of promise in terms of how quickly can we find bugs, how fast can we increase coverage. And in fact, Whisper Fuzz, this is the latest Usenix paper. It received a distinguished paper award in the conference. This happened like 2 weeks ago. Okay, and I just want to finish up with the last paper. So obviously we want LLMs. Without LLMs, there is no talk these days. So we didn't want to be left over. So we tried this. So basically the motivation for this is that, yes, you have this hardware fuzzing framework, you have input generation, you have vulnerability detection, you use, let's say, golden reference model to do differential testing and find bugs. But the issue here is, what if there is no reference model? For processors, we have, let's say, for example, ISA emulators. But if you're verifying a peripheral where, let's say, you don't have the reference model, then what do you do? One option is, okay, I can use assertions maybe to detect vulnerabilities. But then even with assertions, like if you look at them, they're not fancy uh, and kind of scary also. Like you have so many components in it. You have to make sure the constraints are right, the signal names are right, the syntaxes are right. And only when you write all of this in the correct way, you will maybe find a vulnerability. And this is a lot of manual process to do. It's error prone. If you write the assertion itself wrong, then obviously we can't find the bug. So to automate this process, we wanted to see if LLMs can actually generate the assertions for us. And so that's where we developed, we worked on this research where we took a large language model. At that time, there was no ChatGPT. The popular language models at that time was something called OpenAI, Playground, Code Da Vinci models. Like they were the most powerful models at that time for code generation. So we used those. And then we created a benchmark of 10 vulnerabilities using like the hardware CWAs. And then, so basically what we wanted to see was, can the LLMs generate assertions and how good are they in generating the assertions? So we came up with some evaluation metrics. And the most important thing, if you want something out of an LLM, is prompt. Now, if you give a good prompt, then you probably get your answer. But if the prompt is not good, it is definitely not going to give the correct answer. So what we did was we created like 2000 prompt configurations. And what I mean by prompt configuration is, okay, when I'm asking LLM to generate assertion, I will give it a clue. I will give it a context. I will give it an example assertion, or I'll give it like the first few words, like assert at the rate positive of clock, property at the rate positive of clock. And we wanted to see how does the LLM perform when generating assertions with all these configurations. We ended up generating 200,000 assertions for 10 vulnerabilities. And we evaluated the correctness of those assertions. And we obviously noted a lot of interesting things. Please check our paper for all the results. But one important observation was that out of these 2000 configurations, the best configuration, it had 93% accuracy in generating assertions. But the worst configuration had 0% accuracy. And you can see the graph of like how different configurations were performing. So this really highlights that, yes, LLMs work, but we have to be very careful and we need to understand how to make them work for whatever we want. Yes, this is the overall impact of our fuzzers. These are all the publications I covered in this talk. And thank you.
Thank you.
So I will be in the job market next year. I will be finishing my PhD. If you're interested, I am looking for jobs in hardware design verification roles. So just let me know. Thank you.
Thank you.